Okay, so welcome back. So first, I'd like to remind you that in homework 5, there are topic selection that you will make for the final project presentation. This is just select topics that you feel you're interested, and then you are going to discuss with your group in the Blackboard discussion board that you can discuss with your other group member. Okay, but for the homework, you should at least select topic that you feel interested that you like to present. Okay, so that's the reminder that you should start thinking about the topic. Okay, and today I'm going to briefly review some of the corner error correction and topological quantum computation. Yeah, some of you mentioned that it was a bit fast for these topics. Yeah, and I agree that these are somewhat advanced topics. So therefore, it probably was some review. Then I'm going to start this week's topic. It's quantum computing by evolution and by measurement. Okay, so maybe let me just review the most important condition in quantum error correction. So suppose you define your quantum error correction codes, then you can define the projection to the code space. It's really just projection. It projects down to the code space. You run through all the code and project to that. Okay, so if you have errors, this EI is a set of error. So for a given code and a set of errors, the error can be corrected if it satisfies this condition. So meaning the action of the two errors, EI dagger and EJ, if they get projected to the code space, it's still proportional to the projector. And they may be coefficient, depends on I and J. And this is the condition that these errors can be corrected. Okay, this is the most general condition, but you could simplify a little bit by diagonalizing these coefficients, and you can transform to a new basis using the unitary that diagonalize the alpha matrix. Okay, so let's say you look at this new basis and the error is expressed in terms of the sum of the original one. You define a new set of error fk. This condition then is translated to that the action in the code space is really diagonal, right? So if you have different error f, then this gives 0. So in a sense that the picture of the process is that if you have a error, okay, first you define the code space. If you have an error, let's say f1, this may take to some code space here, and if you have other fk, then you take to some other space. This condition shows that these errors take the code space to other subspaces that are orthogonal. Therefore, if you can localize which subspace it is, then you know what to correct back. So that's the essence of the quantum error correction condition. Okay, and we look at Shor's codes also in terms of this. So if you have time, you should review that statement, how we show that Shor's error correction code can correct one error, one qubit error. And many quantum error correction codes are expressed in terms of so-called stabilizer. So they are stabilizer code. These use the so-called stabilizer, and this is the group that contain element in the poly group, and such that each element in S stabilize the code. Okay, this is the definition of the stabilizer group. So the group theory we use here is really minimum. These G's they commute with each other. They really just product of poly. Okay, so these either commute or anti-commute. But in the stabilizer group, all the elements they commute. Of course, -1 should not be in the stabilizer, otherwise you have contradiction. Okay, so this define the code because if you have n minus k constraint, independent constraint, given by the generator of these, generator in the group basically really the minimum set of elements that when you multiply in all possible way that give rise to the whole group. So that's the meaning of generator. But they also mean that they are independent. So you have n minus k independent constraint. This means that you have k qubit that you can encode. Okay. Using n physical qubit. Okay. And in terms of the stabilizer code, the condition error for this set error is that the action ej dagger ek, similar to this here, is not in the so-called normalizer minus S itself. So normalizer basically in this context, the set of element that commute with the stabilizer S, meaning anything that commute with the stabilizer is in the so-called centralizer, but the centralizer in this case is the same as normalizer. So we're not, these are just maybe names that if you just pay attention to the content, basically the two are essentially the same here. So these two are the same in this context. Okay. So basically it just, you have, if you define a group, you can try to find a set so that any element in this set commute with all the element in the set S. That's called centralizer. Okay. Basically, you just need to find these elements. Okay. The error correctable condition using stabilizer means that this product is not in the normalizer minus the stabilizer, meaning that it's either in S or in the poly group, but not in normalizer S. Okay. So yeah, so that basically that's the condition, but basically the idea is that if our error commute with all the stabilizer element, then that's bad because we don't know the effect. We cannot probably infer whether it's an error or it's a logical operator. So that's you don't want it to be in a normalizer. But it is okay that this product is in the S because this is similar to in a closed space, that it has no effect. Okay, but you can really take these two as a condition, right? So just either you use this condition or you use this condition. The only thing that you need to know is to find the set of elements that commute with S. And then you check whether the error combination is in this or not, right? If it's not in this set, then these errors are correctable. Okay. Because we are talking about very general conditions, so it's formulated in a complicated way. But when you apply to Shor's error correction code, you see how it's applied, and then you probably have a better feeling of these error correction conditions. Okay. So yeah, maybe I mentioned the group theory. The group theory is really minimal. The poly group, let me mention again, is really just product of poly, and it could be plus minus 1, plus minus I coefficient. That would also need to be included in order to form a group. Okay, and this is G1, meaning you have 1 qubit. G2, you just take all possible product of 2 qubit of single qubit poly, and form 2 qubit product of poly. So that's and you have n qubit. This is called poly group. Gn that we use, right? Gn is n qubit poly group. Yeah, and if you still do not have a sense of what a group is, and just remind you really the basic. A group is a set, let's say maybe 0 and 1, and you also have a group action, and this one, it says that it has a identity element such that this is always this. In this case, 0 is the identity element. Okay. In terms of if you want to use multiplication, you will probably use 1 and minus 1. So 1 times minus 1 is always minus 1. Okay. And you always have an inverse. So inverse of minus 1 is self. So this is really the simplest group you can have. Okay. Beyond the trivial, just identity. Okay. So these groups are usually called Z2. And if the group multiplication commute, then it's called abelian. Like 0 plus 1 is 1 plus 0. That's abelian. So addition is abelian. Also multiplication is also abelian. Matrix multiplication is not necessarily abelian. So when we look at matrices, unitary group, they are not abelian. And there's also the property of closure, meaning that if each of the group element G and G prime are both in G, then their multiplication is also in G. So this is the group closure. You also have the associativity. If you have 3 group elements, you can first multiply the first 2, followed by the third. Or you could do for the second and third, and then you take the first and multiply by that product. Okay. I hope that this will alleviate your worry about group theory. Really, these are simple. Even just to define that, it's simple, but when you look at a statement, it may seem complicated. But if you look at real example, then it should probably be not that difficult. Okay. So maybe you can raise hand to let me know. Have you seen any of the group theory or the definition of group? Use raise hand feature to let me know. I see 1, 2. 3, 4, 5, 6, 7, 8. I would say 2/3, maybe 2/3 of people confirm that you have seen the group theory, some perspective of group theory in the past. Yeah. What I want to stress is that the way I'm doing this course is I try to use as little math, complicated math as possible. When I list it, I just take that as granted. So these two statements that I take them as granted, I don't have time to go through the proof, and I don't think that's necessary. You should do that yourself. You can look up these books. But I provide you some intuitive pictures. Because it's not possible to learn everything from scratch. So we have to assume something. If that's something we never learned before, we would take it as given, and then we always refer back to that statement. Okay. Yeah. And in fact, we didn't use that much group theory. Okay. An example of stabilizer group is this toric. Toric, you have on the two-dimensional lattice, qubit on the edges, and we have defined two types of operator. One is star operator, is product of X on edges crossed by the dual loop. Okay, and the B operator is product of Z on the plaquette. And you can see that these commute because if you have a star operator here, they overlap twice. Okay, so there are elements that they commute, and therefore the toric has a stabilizer group generated by all these, meaning that the product of these AS and BP in any way one is an element in this stabilizer group. Okay, and we have noted that by multiplying this over all the vertices, the AS is 1, meaning that there is a constraint. Right, there's one constraint on A, there's another constraint on BP. Okay, so therefore there are two encoded qubits on torus. So that's why you have this toric. Okay, and we have also deduced the logical form. They basically form product of poly operator X or Z along big circles, right? And if you want to find a normalizer, these are the group that contain element that came in with all the stabilizer, but not in a stabilizer. So meaning that this has to be non-trivial loop up to these stabilizer local loop or local stars. So this means that in terms of error correction condition, the normalizer minus this stabilizer itself is extended object, right? Meaning that it has to form big loop. And for single or a localized error, so if I have a Z like this, and I have X, when you multiply these localized objects, it will not be in this, right? So that's one example of that. So this means that the toric has really large code distance. So the distance is as large as the linear size. Okay, so the larger the code distance, the better the error correction property. Okay, and remember in our surface code, I started using this, but in fact you want, so this is just for discussion. I start with pair pocket of defect, but in fact you want this to be big. So you want, so this on the surface code, because this area, so that, or the perimeter to be more precise, and the link between the two will determine the code distance. So the bigger the better. But that also means the fewer number of qubits you can get. So there's some trade-off. Okay. And we also mentioned a few annual models. For the Torico, they are for annual.
Sorry. What's the PC here? Last line.
That's the ground space. That's the code space.
Yeah. In mathematics, in group theory, we talk about stabilizer. We usually use stabilizer of a group member, but here we use.
G is a group member.
No. I mean PC.
Psi is for psi. Yeah, so maybe there's a difference between the math and the physics language here. So we mean the stabilizer, they are elements. Stabilizer is a group, and we have element G in this stabilizer. The definition is that these define the code space. This psi is in the code space. Yeah. So this may be slightly different from what people use in group theory. I don't know. Yeah. So what exactly did you define as a stabilizer?
Thanks.
Can you say that? What exactly do you use in math?
Math just group theory. I just studied group theory. I don't know what to
It may
use.
be some object that is left invariant by the group action.
Yeah, maybe this is a group action on some set.
Yeah. So, but I'm defining exactly what I mean here, right? So it's all here. So there may be, I mean, it's not possible to find certain definition that does not sort of has conflict with other definition, but I'm trying to be consistent. Yeah. So you define a group S. Group S, this in this case is abelian group. They commute with each other. Does not contain -1 identity in that group. And we call it stabilizer group because when we do that, we always want to have a code, right? So that code is defined by this. So maybe in terms of physics, this act on that return the cell, meaning that it's stabilized by that. So that's why people call this a stabilizer group. Yeah, but this error correction code in this formalism, I would say were developed by physicists and computer scientists. So the language is pretty standard there. Okay.
So now I'm confused. So all the single star and the simple placket are stabilizer.
Element. When we say stable, we generally say it's a group. Okay. And AS is an element in that group. AS and BP is a group element, right?
Yeah. So A and B generates the stabilizer group.
Yeah. Any product of AS and BP, right? Because you have many anywhere, right? So it could be here and it could be there. So you take any product of these AS and BP, okay? That generate the group. And we already counted, yeah, this is there are n square of this, right? So on each vertex and on each pocket, there are n square pocket. But the number of edges equal to n squared times 2, but we have two constraints, right? If each one is independent, then it uniquely determines the state. But since there are two constraints, so that means there are two fewer two fewer independent elements in the generator. So that's because these two constraints in the product that allow us to have 2-qubit encoding. So this is 2 encoded qubit. Okay. Yeah.
I can see here are two identities to you have to preserve this true identity, but I cannot see why there's only these two. Can you prove this? There are that's the only true constraints you need to follow.
I think you can prove that's the case. Yeah. Maybe with a bit more mathematics, you can make it really rigorous. Use homology. The chain, 1 chain, 2 chain. I don't want to go through that. Yeah, but I'm not a mathematician, so I don't claim everything to be rigorous. What I told you here, but at least it's intuitive. You can, if you want to see that they are more constrained, you need to have something else that multiply to identity and independent of these. Right? I think if you look close enough, you would convince yourself, right? The AS, okay, if we want, the AS are on these vertices, right? Let me choose circle. These are local, right? If you have 1 here, let's say I have 1, I want to cancel this one, I need to have another next to it, then I generate many other things I have to cancel, and you should convince yourself that the only way that I cancel is I extend it to everywhere.
Okay.
That you could also do that for the pocket. Yeah. So I think you can convince yourself. I don't claim that this is rigorous in the sense of mathematics. Yeah. So if I have to do that for every statement, then I don't think I can even go through the week 1 lecture. I would have to define a lot of things. Yeah. Okay. Annual models. So for the Topological, there are 4 annual, but these are abelian. So meaning when they break, they only give rise to a phase. And these are the fusion. The only thing that should be noticed is that E fused with M give rise to F. So F is a fermion. Okay. And these are created out of vacuum. Pair of them then fuse back to vacuum. Okay. And we also mentioned one particular annual model, meaning the Fibonacci anyon. It contains only one non-trivial one. And the fusion looks like this. You take 2 Fibonacci anyon, it returns either vacuum or the Fibonacci anyon itself. Okay, and the reason it's called Fibonacci anyon is that the number, the coefficient in, for example, in this identity, is, as you break more, as you fuse more anyon, is give rise to this Fibonacci series. Okay. And we also learned the Ising anyon model. It has 3 anyon, the identity, psi, psi is a fermion, and sigma is the Ising annealer, the non-trivial one. And the fusion, maybe the non-trivial one are these two, fermion and the Ising fused to Ising. So you could regard this as a fermion and this Mariana mode, and it still is a whether it's occupied one or not. These two Mariana mode can, yeah. So maybe I should say, yeah, two Mariana mode allow you to not occupy a fermion or occupy a fermion. This is just saying that sort of a fermion can be absorbed into a condensate. If you have a Mariana mode, it doesn't change that. Okay, maybe it's clear if you go back to our model with vortex, two vortex. Each one has a Mariana fermion mode, zero mode, and two of them form a fermion. And these come from P-wave superconductivity. So in the sense that there is a condensate of Cooper pair, maybe fermion. Okay, but you can just take these as mathematical definition of fusion. Okay, and we mentioned that the Fibonacci annealer is probably the one that's the most ideal because it is universal. Just by braiding, you can get any single qubit gate. You can get CNOT gate approximately. But this is very difficult to find in the real world. Okay, so the reason that these are called topological quantum computation is that these braiding, you can braid. So braiding, right? You braid these two. If you do, for example, like that, it doesn't matter the precise particle, right? Do you move it a little bit or do you move it to the left? As long as you form a braid topologically, then you would always give the same action. So that's why it's called topological. It's topologically protected. Okay. Ising anneon is not universal, but their gate property are easy to see. For example, you braid the particular way we encode it. You braid the second and third particle twice, you get X gate, and you braid pair of these, three pair of these, you get a control Z gate. They are not universal, so therefore they need extra work, such as the magic state distillation, to be able to do universal quantum computing. Okay, so I would say the second one is easier than the first one. At least there are a few candidate physical systems that can realize these Ising annealer. But there's only one possible system in fractional quantum Hall effect that might realize the Fibonacci annealer, but it's not yet confirmed. There's no experimental evidence. Okay. The third one that we mentioned is the torical, but on planar geometry. It's called surface code. I think this one is closer to reality. You can engineer these pair of defects, and you braid around. You can get a gate. This is CNOT gate, and of course, this is the only topologically protected gate. Of course, there are other things we need to do. For example, Who remember what is the gate that we can realize using this? So we have a pair of defect, and we think one of the defect to really just a point or a pocket, and then we rotate. We can add a anealer, do rotation, and the measurement.
X.
This I think in the particular way, it's a Z rotation. Because we shrink that to a pocket, and then we do some CZ gate, and we add an anealer, and we do some CZ gate. I don't exactly remember the pattern, and we perform measurement. Yeah, so that's the Z rotation. The X rotation we did is we shrink it. Okay, so this, what I should say, these are the primal defect. Because if you use the DOA, this may be an X rotation. Okay. What about this one? What did we do for this one? Who remember? So here we combine the Z rotation, right? Z rotation is this part. And this part is X creation. So basically, we have a Z rotation on a plus state. So this would give you a phase state, right? So that's a noisy phase state. So inject noisy phase state. This one is what rotation? This one is the X rotation. So because we are bringing, this is a X, logical X, we shrink that into really a single point, and we rotate directly on a single qubit. Okay. And this circuit here, if you have a wise eigenstate, you can do a phase gate. So this is the phase gate, but this is in the X basis. Okay. There's also the T gate. If you have this kind of magic state, you would be able to do the T gate, but this in the X basis. Okay, meaning that with a little bit extra work, you can get a universal quantum computation and topologically protected, in the sense that you use some of these topological protection and a high fidelity magic state distillation. So, and you will really get a high threshold, error threshold. Okay. I think that's the review of probably the last 2 weeks content. So any question on this? Okay. So yeah, so this week we're talking about 2 different ways of understanding quantum computation, or 2 different framework of building quantum computers, if you will. But let me just remind you that we have learned the circuit model, right? And this is what we're going to talk about today, the Adiabatic, which basically you use Hamiltonian. So this is closer to quantum mechanics than other model. Closer to the essence of quantum mechanics by really just the Schrödinger equation. Really just evolving Schrödinger's equation. Okay. As I demonstrated here, when you evolve in time, somehow maybe the state would follow along, and then you can get to the final answer that you want. But we'll describe this more in detail later. And we have done also the topological quantum computation. But as you see, it's really just using anyons and braid around to get quantum gate. So in some sense, 3 is just a way to do 1. But this is one that Microsoft is betting on. And Google sort of use some hybrid 3 and 1, meaning that they're using surface code. So let me maybe put tag here. So Microsoft currently is probably betting on using Anyon. Google is doing the surface code. Okay. And there is also another way of doing quantum computation is you only measure local spins. This is called measurement base. So, and these two are the topic of this week. And there's also a company called PsiQuantum, which use a photonic system, and many use this measurement base. Okay, so let me go directly to the adiabatic quantum computation. The idea is very simple. If you have some problem you need to solve, so there's a Hamiltonian corresponding to that. Maybe you want the ground state of this Hamiltonian, but it's maybe very difficult to solve. So what you do is you combine that with an initial Hamiltonian, which is simple, that you can choose. And ground state is also simple. And what you do is just write down a Hamiltonian that depends on time. Maybe when t is 0, is this initial Hamiltonian. When t is the capital T, the final time, that's the final Hamiltonian. And in terms of Schrödinger equation, this is how it's going to satisfy. Okay. So this is the Schrödinger equation. And basically what it says is if you let it evolve, it should follow, if you start with the ground state, it should follow it through to the ground state of the final Hamiltonian, provided that there's a gap. Okay. And you should also not evolve too fast, because if you evolve fast enough, this state representing the state of the start representing the state of the particle may jump up, right? It may go up. So okay, but if you regard the evolution, basically what it does is you start with the initial Hamiltonian, you have some small t1, it evolved by really small amount of time that evolved here, and then using a slightly different Hamiltonian evolved, right? You can imagine it's discrete evolution, but you take the limit to 0. And this is a solution of this Schrödinger's equation. Okay. Formally, if you are a physics student, you've probably seen this. It's a time order integral of this. You integrate this time-dependent Hamiltonian, but you need to do it in time order. But this is exactly what I wrote here. Okay. And this is just a notation. So if you're not a physics student, so it's probably not that rather than that you need to solve this, you don't need to solve this. You just need to remember this is the solution. Okay, this is just what probably you need. You can imagine that a quantum computer may also approximately do that, right? You just evolve with this Hamiltonian for small time, and then you choose a second Hamiltonian, evolve with a small time. And as long as this time is chosen small enough, this would approximate the evolution of this Hamiltonian Schrödinger equation. Okay, and it was shown that using this adiabatic quantum computation, adiabatic evolution, you can use that to simulate any quantum circuit. So meaning that it's also universal. So to be more precise, if you're given a circuit, you can construct a Hamiltonian to achieve the same computation. Okay, so this has been proven. So maybe one should ask is how fast, or in a sense, how slow should we go? This is called adiabatic because it means that you should not evolve fast enough, you should go slowly. So how slow should we be? So meaning how large should this time, capital T, be? So it's given by this. So we want, we start with the ground state of the initial Hamiltonian, right? And we evolve to the final. So I'm going to use this reduced time variable s. At s equal to 1, that's the final state. This is the final eigenstate. Okay, ground state. Ground meaning 0 is here, 1 is the time, and this is the evolved state. So intuitively, if this time goes to infinity, right? If I go really, really slow, my evolved wave function at the end should be just the ground state of that final Hamiltonian. The overlap should approach to 1. Okay, so that's basically this is what the so-called adiabatic theorem. But we can make it more quantitatively to make it so that we have estimate of the error. Suppose we want to estimate the difference of the two. We say if we want that difference to be smaller than some threshold epsilon that we set, and we can ask the question, how large should the time be? It turns out this time has to be bigger than 2 over the epsilon. This is the error threshold we set, and times this complicated expression. Okay, this is probably the most complicated expression about the time. We were not going to use this, but I just want to show you that there exists such a rigorous statement. But you can see that it's inversely proportional to delta square, evaluated at 0. Delta is the spectral gap, meaning that this is delta. Okay, that's delta s. S is the coordinate along the time. Okay, but you can see it's square, square, cube, and square. So there is a simplified version. The simplified version is that it's less precise but easier to remember. Is that the change of the Hamiltonian? If you evaluate the ground state and the first excited state, you see how much they go from, let's say, go from this to that, through the Hamiltonian, the change of Hamiltonian. if this change, we want this to be tiny, right? And how tiny it should compare to the gap. If the rate goes from 0 to 1, this rate through the derivative of the Hamiltonian, if that's compare the gap square, if it's small enough, then this condition is satisfied. This condition will be satisfied. Okay.
So quick question. Does it work the other way around? Meaning if we're started with the excited state, then can we somehow jump?
It should also satisfy. Yeah.
Okay, so we may purposefully start
as long as there's a gap. So yeah, so the adiabatic theorem goes stronger. Like if you have all these, as long as no level crossing. If you have a crossing, then you cannot say anything. As long as these gaps are there, if you start with a first excited state, you should stay with first excited state. Yeah. If you start,
Sorry. Can I finish first and then one? Is it possible for the first excited to drop to the ground state?
Yeah, it's all possible. Okay. Yeah, you can go down, you can go up. So if you're at the ground state, it's only staying here or you make transition up, right? But if you are here, you can make transition down or up. Yeah.
Okay, I see. Thank you.
I have a look.
Yeah.
Can I see the previous slides?
It's the same as this one, right?
Have a look at the previous slides.
It's the same.
Yeah.
This is the same as this top here. But this, I don't want you to remember this. I don't even remember this myself. I just I don't memorize them. I just look up them when I need it. But this is maybe the most more simplified and easier to remember. You can see that this is the Hamiltonian derivative with respect to time, right? It's the rate how this, so I'm saying the rate how this make the transition through the energy should be smaller than the minimum gap square times this error threshold that you set. Okay. Yeah. Does that make sense? If the transition rate is slow, in some sense, this is the transition rate. It's small, then we will not make much transition to the excited state. Okay. Yeah. So if I go back, basically what adiabatic computation is, you need to find two Hamiltonian, and you interpolate that, and you want the gap between them not to close, right? You want there's still a finite gap between them, but this gap may become smaller and smaller as you have more and more qubit. Okay, and the smaller the gap, the slower you should go, right? And this t expression basically just tell you the time factor, how slow I should go. Okay, this is really precise, this expression here. But if we ignore many details, this would suffice. This condition would be good enough for us. Okay. Yeah, so we're going to apply this. Look at one specific example of Grover. Okay. So any question?
So E0 and E1 are qubit 0 and 1.
So E0 is the ground state, E1 is the first excited state.
And the delta is the energy difference between them.
Yeah, but this, so the top expression because we're trying to make really conservative estimation, we want to find the maximal rate, right? This is the maximum. I want to maximize over all region the transition rate. I want the maximal rate to be smaller than the minimum gap square. This minima is minimi over all region. Okay. Does that make sense?
Yeah.
Yeah, because we just want to give one number, right? So I would choose the worst case scenario. I take the largest rate divided by the smallest gap square. That would be could be a big number. I want that big number to be smaller than my error threshold. Okay. Yeah, so we're going to apply to Grover, and we've seen Grover before, so I don't want to go through the detail, but it's really just some mark item and then you have oracle and put a minus sign and you do the reflection around the mean, right? It looks like a rotation in some two-dimensional subspace. This two-dimensional subspace, you can imagine, I mean, we've seen this before, as a mark space and the mark space, right? It's really just in that two-dimensional subspace, okay? So I'm just listing these that we have seen before, but I don't want to go through the analysis because we don't need the detail for that in our Adiabatic quantum computation. So we're going to assume, but just remind you some definition S. Unfortunately, this is the S that we used before to denote the state. And we also use the parameter S defined to be T, small t over capital T. Unfortunately, they're the same symbol. Okay. And we show that the Grover has a quadratic speed up, square root of n. So in the example of using Adiabatic quantum computation, we're going to just consider there's only one mark item. Okay. So if we want to do the Grover search by adiabatic evolution, we know initially we start with this plus plus state. We denote this by S. Okay. This is the superposition of all items. So in order for this to be a ground state, we simply take the Hamiltonian to be 1 minus the projector, right? If you're orthogonal to S, you will get energy 1. If you're this, then you get energy 0. Okay. We're going to assume there's only one marked item labeled by M. So assume, yeah, we're going to choose the final Hamiltonian so that this will be the ground state. So similarly, we choose this. Okay, so the final Hamiltonian is M, identity minus projector to M. So this M is what we're going to find. And we know the M is one of the object and S in the superposition of n objects. So their overlap is 1 over square root of n. So I'm going to label this as A. Okay. So the time-dependent Hamiltonian, as I said earlier, we're going to interpolate between the initial, the projector down to the S, and the final projector down to the M with a minus sign. We're going to add these. So we can ignore these identities. So there's identity here, but what's important is the two interpolation from S to M. Okay. So, and these are the two-dimensional space. So remember in the one that before, this is M orthogonal, and this is M, and we have S here. The Grover rotation is rotating this, okay? Okay, so given that we have this Hamiltonian, we can diagonalize that, right? This is a Hamiltonian spanned by two vectors, two projectors. So we can diagonalize in the space spanned by M and S. But these two are not orthogonal, so it's better we choose a basis that they are orthogonal. Okay. So first we have to construct M perpendicular. So given M, how do we get the M perpendicular? We get it from S and subtract component along M, right? And we will get M orthogonal. Okay, so this is what we're going to do. We're going to define this M orthogonal to be the S subtract the projection to M, and we know the projection, the overlap is A. So if we subtract this component, then this will be M orthogonal. And we assign a coefficient C so that M is normalized. So this C is needed to normalize. Okay. So I'm basically subtract the component M, right? So you can verify this is indeed orthogonal to that. This is orthogonal, right? It should be 0, right? Because if you take that M inner product with S, A, M inner product with M, and this is A, this is 1, it's normalized, so therefore this is 0, okay? So we just take these two vectors, M and M perpendicular, and we want to write this Hamiltonian in that basis. So there, it's a 2x2 matrix. You take M and M, perpendicular M, and particular N and M. So basically this is in this basis, M perp, this one M perp. And you compute all 4 combinations, right? And this is a straightforward calculation, right? You have M here, so you have H here. Basically, this is the one that's important part. You just take this and then calculate this, and this is the matrix that I get. It's really just straightforward. So maybe I just do one for you. So if I want to calculate this, how do I do that? It's really taking that and the Hamiltonian and sandwich this way. It's Sn minus T M, and this is 1. And this is A square. So that's why I get minus psi over O here, and this 1 minus T A square plus T over T. Okay? And you do this for all the other 3. In fact, these 2 are the same. And you can get this matrix. It's a 2x2 matrix, so it can be easily diagonalized by hand. And when you do that, you can get the energy, right? Diagonalize and get eigenvalue. You can get the gap as a function of T over T. And this is what we get. This is the gap. It's just easy to define this T over capital T as a parameter S, and the gap as a function of the S, the normalized the normalized time has this form. So the gap, this is the gap. And you see that it's the smallest in the middle when s equal to 1/2. S equal to 1/2, this is a factor of quarter that cancel this, and 1 minus that cancel out. So the minimum gap is exactly 1 over square root n. Okay. And this square root n should be the speed up in Grover, right? However, if you look at the time, we are running linearly in time. So our time runs linearly because we use y minus t and t, right? Basically, you linearly increase this, you linearly decrease that. So we are not gaining any speed up. Okay, that's the intuitive picture. We didn't gain any speed up at this moment. A more rigorous is to basically calculate the time or use the criteria that to estimate this. So remember, this is the rate, weighted rate. I want to maximize this, but I first take a look of the dH dt. I find that this is just a constant, right? It's really just from here. Take the derivative with respect to time, you get this 1 over t factor, projector to s, 1 over t factor projector to m, and the difference of the two. So really doesn't matter what the exact form of ground state and static state. The maximum of this would be of order 1 over t, right? So this means our criteria is that I move t. So this is really 1 over t, and I move t to the right hand side, and then I'll become the left hand side. So this means t has to be greater than 1 over the gap, minimum gap square, over this epsilon. Right, 1 over minimum gap square is 1 over n, right? Because this is the gap. So we use this, right? So meaning that our time has to be proportional to n, and that's why we don't get any speed up, right? So this is basically what I said. We ran down linearly the first term and we ran up the second term. So it doesn't matter the gap. We always run linearly, right? So therefore, the natural question arises: how do we change our time, the ramp up, so that actually we take into account this is small gap, right? This small gap. So gap is small, so we should run slower. But when the gap is large, we should run faster, right? So maybe this indicates we have another way. We rescale the time. We can run faster in the beginning and slow down in the middle and run faster toward the end. So that sounds reasonable. To make it quantitatively, what we do is, let's say this is the rate that we're going to run the reduced time. So we're not going to, so s is no longer this. We're going to just define as a function, okay? So we want this rate of change in the s to be proportional to the minimum gap square. That's really just one naive way of doing that, right? So that in this way, when it's in the middle, the gap is small, so the change of s will be small. Okay, so you just expand this and you can do the integration. So let me just rewrite this condition here. Basically, you have this, you can find S of t or t over of s. And if you want to estimate the total time, it's basically integration of little t from 0 to t, but you can turn it express in terms of s, right? Basically ds over epsilon delta s square. You can analytically integrate this, and this is the final expression. When n is large, so arctangent is large, close to 1, pi over 2, for example. Yeah, it's close to pi over 2 when this is large. And this n over square root of n minus 1, roughly square root of n for large n. So meaning that the total time we had to run scale square root with the number of items. Okay, so we get a speed up. Okay, so here is how the time need to change. So you see that this is the gap. Okay, in the beginning is large gap, so we run faster, right? This is the real time, but our s, we're going to increase the s very fast in the beginning, and we start to slow down in the middle and then speed up again. Okay, so that's the new time schedule that we're going to use in this Grover modified Hamiltonian. Okay, and we get the speed up. Okay. So any question on this little model? It's just really demonstrate in principle that the square root n speed up. Okay. So I want to mention that I use adiabatic, but it's also possible to use measurement. This is what usually is called Zeno effect. Maybe many of you should have heard of Zeno, right? It's sort of claim that an arrow to go from the initial to the final. In order to do that, you need to pass half of it. And in order to pass half of the middle, you need to pass half of that. And that means there is infinite sequence. And therefore, Zeno claimed that it's not possible for the arrow to reach from one to the other. Of course, this is absurd, right? Because even though we have infinite intermediate middle point, you add up to a finite number of time. Okay, that's a cartoon just to make fun of Zeno. That. But in terms of our adiabatic quantum computation, it's also possible to use measurement instead of let it evolve. If we have a way to measure the projection to energy eigenstate at any instantaneous point, time point. Okay, and we have a way to do that, but there's also other methods. So the picture is that I discretize the time, and I perform I would start my system in the ground state of the initial Hamiltonian, and I measure eigenstate for the Hamiltonian right in front of it. So because I'm only moving time slightly, there is a large overlap of the initial ground state to the next delta t ground state, and in a way we would have high probability the ground state would become this ground state, and you could drag along in a discrete way. So that's another way to implement the so-called adiabatic quantum computation by measurement. Okay, this is just a comment that there are also other ways. So, but this is I would say a research area. A related subject that I want to mention is the D-Waves quantum annealers. You probably have heard of D-Wave. They have 1,000, 2,000, and recently they have 5,000 qubit quantum annealers. These are machines that have qubits that are much noisier than other circuit-based one. Okay, such as in IBM, Google, Rigetti. But their idea is to sort of manufacture large number of qubits, and they are coupled in a way so-called chimera graph. So these are the chimera graph, the example of chimera graph. These represent how the qubits are connected to each other. So locally they are highly connected, but it's loosely connected to a neighboring group. Okay, and you can see the detail at this documentation there. Okay, but they also have their own software. It's called Ocean Software Development Kit. It's also Python based. This is their software part that interact with what they call quantum processing unit, their QPU. It can also interact with a classical computer so that you have some hybrid way of controlling that. And they can be used to solve some optimization problems. So we have seen something similar before, max cut, traveling salesman problem. And we use binary variable X, and there's some weight or some local field. And we write that in terms of classical Hamiltonian, and we can turn this into a quantum Hamiltonian. So you can turn this problem Hamiltonian using the mapping to sigma z. So the X as binary variable. You turn this into poly sigma z. So these define binary quadratic model, that classical problem that you want to solve. And the way that D-Wave solve these problems is to start with the initial Hamiltonian. That's simple, like transverse field. And then you add, really just add this problem Hamiltonian. Or you could define more generally some coefficient so that A goes to 1 as time in the beginning, and B goes to 0. And then at the end, A goes to 0, S goes to 1, B would goes to 1. Okay. So this is the problem set that they can solve. As long as you can turn it into binary quadratic model, then they will be able to use the so-called annealer to start with the ground state and then gradually change the time schedule. So hopefully it would end up with the ground state of the final Hamiltonian. But as I said, because their machine are noisier, so they probably take advantage of the large amount of qubit that they can solve large number of problems. But it could be that the answer they get, some fraction of them are not really the ground state, maybe ecstatic states. So that there will be certain fraction of the solution that are in the ground state. Okay, and that this is a schematic diagram of their annealer. These are the problems you want to solve, and you can turn this binary quadratic model, that's listed here, and use their machine to solve, and then try to get from the quantum state to measurement and to check the solution. Okay, so we will not be able to go through any of the example tutorial with D-Wave machine. If you're interested, this is a link you can go. Okay, and it could also be a final presentation if any of you are interested. This could be subject that you could give an example of the notebook and how it runs for one particular problem, etc. Okay, So I guess that's what I want to say today, right? So we cover circuit model previously, topological computation, and today we cover the adiabatic. So next time we'll discuss the measurement base. Okay, so I'll stop here. Any question? Okay, if there's no question, I'll see you on Wednesday.
Thank you.
Thank you.
Thank you.